What is today's lesson? Let's see elements in column 15 and column 17 in the periodic table. Column 15: nitrogen, phosphorus, arsenic, antimony, bismuth, moscovium. And elements that belong to column 17 are fluorine, chlorine, bromine, iodine, astatine, and tennessine. We know that elements of any specific column are almost similar in properties. Based on this point, let's write today's lesson. That is, phosphorus reacting with chlorine can form phosphorus trichloride and phosphorus pentachloride. As nitrogen belongs to the same column, so nitrogen is supposed to form similar types of compounds like this. Nitrogen with chlorine is supposed to form nitrogen trichloride and nitrogen pentachloride, but actually nitrogen trichloride is formed, but nitrogen pentachloride is not formed. That is, today's lesson is phosphorus with chlorine can form phosphorus trichloride and phosphorus pentachloride, but nitrogen of the same column with chlorine can form only nitrogen trichloride, but nitrogen pentachloride cannot be formed. Why? This is today's lesson. Let's go to the detail. First of all, let's see electronic configuration of chlorine. Chlorine 17 atomic number. Electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. Electronic configuration in box system we can write in the outermost shell 3s and 3p. 1, 2, 3. This is 3s that contains 2 electrons, and 3p, 3px, 3py, and 3pz. In these degenerate orbitals, 5 electrons will enter. According to Hooke's rule, firstly, in degenerate orbitals, 1 electron will enter each, and then the orbital will be paired. That is, in the outermost shell of chlorine, there are 3 pairs of electrons and 1 unpaired electron. In these compounds, hybridization of chlorine may be showed in this way. That is, chlorine here undergoes sp3 hybridization, and hybrid orbitals are chlorine. This is one hybrid orbital, this is one, another one, another one. That is, total 4 orbitals take part in hybridization, and after hybridization, total 4 orbitals are formed, which are similar in shape and of same energy. So these 4 orbitals are hybrid orbitals. Out of these 4 orbitals, 3 orbitals carry 1 pair of electrons each, and another orbital carries unpaired electron. Simply we can write that chlorine 3 pairs of electrons and 1 unpaired electron that remains in sp3 hybrid orbital. Now let's see electronic configuration of phosphorus. Phosphorus 15. Electronic configuration is 1s2, 2s2, 2p6. 10 electrons have been distributed. Now, electrons will enter third energy level 3s2 and 3p3. Total 15 electrons. As phosphorus is the element of third period, phosphorus has 3 sublevels in the outermost shell. So it has 3d orbitals, but 3d orbitals remain vacant because up to 3p orbitals 15 electrons have been distributed. Now let's write electronic configuration of phosphorus in box method. Phosphorus outermost shell electronic configuration 3s, 3p, 1, 2, 3, and 3d orbitals 1, 2, 3, 4, 5. 3s orbital contains 2 electrons and 3p orbitals contain 3 electrons. In the degenerate orbitals of 3p energy level, 3 electrons enter one by one. Now let's see formation of phosphorus trichloride molecule. Phosphorus trichloride. Here, phosphorus is sp3 hybridized. That is, phosphorus sp3 hybridization occurs here. Then the orbital structure will be phosphorus will have 4 hybrid orbitals 1, 2, 3, and 4. One orbital will contain one pair of electrons and another 3 orbitals will contain 1 electron each. These orbitals containing 1 electron will overlap with the orbital of chlorine in this way. This is the way phosphorus trichloride is formed. This is trigonal pyramidal in shape. In this way, phosphorus trichloride is formed. Now let's see formation of phosphorus pentachloride. Phosphorus pentachloride. Here, phosphorus is sp3 dehybridized. The process is like this. When phosphorus gets excited, then one electron of 3s orbital will shift to the vacant d orbital, and then we get 3s with 1 electron, 3p orbitals with 1 electron, and 3d orbitals 1, 2, 3, 4, 5 with 1 electron. That is, in the outermost shell of phosphorus now, total 5 electrons, unpaired electrons. Here, S, P3 and D hybridization occurs. So, in phosphorus pentachloride, phosphorus is sp3 dehybridized atom and its shape is like this. 5 orbitals 1, 2, 3, 4, 5. 5 orbitals are formed. Here, total 5 orbitals take part in hybridization, and after hybridization, 5 orbitals are formed. With these 5 orbitals, chlorine forms bond in this way. This is the way phosphorus pentachloride is formed. and its shape is trigonal bipyramidal. Here, phosphorus pentachloride is formed because of the presence of d orbital, vacant d orbital. Here, vacant d orbital present. That is why one electron from 3s orbital shifted to the vacant d orbital, and as a result, 5 unpaired electrons are produced. With these 5 unpaired electrons, phosphorus forms phosphorus pentachloride with 5 chlorine atoms. So, because of the presence of vacant d orbitals, phosphorus can form phosphorus pentachloride. Now let's see formation of nitrogen trichloride and nitrogen pentachloride. Nitrogen 7 atomic number. Electronic configuration is 1s2, 2s2 and 2p3. This is the electronic configuration of nitrogen. Let's write electronic configuration of nitrogen in box method. 2s and 2p, 1, 2, 3. 2s orbital contains 2 electrons and 2p orbitals contain 1 electron each. This is the electronic configuration of nitrogen in box method. Here we see that nitrogen has 3 unpaired electrons and nitrogen has no vacant d orbitals because nitrogen is the element of second period. That is why in the outermost shell of nitrogen there are 2 subshells, S and P, but no d subshells. That is why nitrogen has no vacant d orbitals. Now let's see formation of nitrogen trichloride. Nitrogen trichloride. Here nitrogen is sp3 hybridized. Nitrogen sp3 hybridized. Orbital structure is this 1, 2, 3, and this is last orbital, sp3 orbital. Out of these 4 orbitals, one orbital contains 1 electron pair and other 3 orbitals contain 1 unpaired electron each. That is, this orbital contains 1 electron, here 1 electron, here 1 electron, and with these orbitals containing unpaired electron, chlorine forms covalent bond in this way. So this is the way nitrogen trichloride is formed. Here shape of nitrogen trichloride is trigonal pyramidal shape. Now let's see whether nitrogen pentachloride formation is possible or not. Nitrogen pentachloride. Here, to form nitrogen pentachloride, nitrogen will have to carry 5 unpaired electrons to form nitrogen pentachloride. But in the outermost shell of nitrogen, we see that there are 3 unpaired electrons and 1 pair of electrons. In this case, there is no chance to break this pair of electrons because in nitrogen there is no vacant d orbital. So there is no scope to increase number of unpaired electrons. That is why nitrogen pentachloride will not be formed because of the absence of vacant d orbitals. So phosphorus trichloride is formed, phosphorus pentachloride is formed because in this case phosphorus uses vacant d orbitals. Nitrogen trichloride is formed, but nitrogen pentachloride is not formed because nitrogen has no vacant d orbitals and there is no chance to increase number of unpaired electrons using d orbitals. As phosphorus pentachloride is formed, similarly phosphorus pentaiodide may be formed, but phosphorus pentaiodide actually is not formed, because we know from top to bottom along a column in the periodic table, atomic size increases like this, and position of iodine is fluorine, chlorine, bromine, iodine, astatine, tennessine. So atomic size of iodine is very large. That is why around phosphorus 5 iodine atoms, accommodation of 5 atoms, iodine atoms becomes very tough. Because of the larger size of iodine atom, 5 iodine atoms cannot be accommodated around phosphorus. This is the reason phosphorus pentaiodide is not formed. Rather, phosphorus triiodide can be formed. So, phosphorus trichloride, phosphorus pentachloride can be formed, nitrogen trichloride can be formed, but nitrogen pentachloride cannot be formed because of the absence of vacant d orbitals. Again, phosphorus triiodide can be formed, but phosphorus pentaiodide cannot be formed because of the larger size of iodine atoms. Now today, thank you very much.